All right, next up, we also have a remote presentation. This is coming from Stanford this time. Guillermo Angeris is going to be presenting analysis of Uniswap markets. And Guillermo, take it away.
Hey, hopefully you can see the slideshow and stuff.
Yes, that's good.
Cool. Hey, yeah, so hi, I'm Guillermo Angeris. I am a PhD student at Stanford. I guess technically, I think at MIT, they call me a lifer because I've done my bachelor's and master's as well. So anyways, this is work that I did with HT, Ray, and Tarun from Gauntlet and Charlie from Paradigm. And in this work, essentially, we present kind of a weird economic analysis of Uniswap markets, which I think has recently gained some notoriety by being part of a BZX attack, quote unquote. But anyway, so I guess to start with, okay. So first things first, what does Uniswap actually aim to do, right? This is generally called the pricing oracle problem sometimes. The idea is, look, we need to find a way of measuring the price of an asset. This is pretty easy, right? You just stop someone on the street and you say, look, how much are you willing to buy this thing for, right? And if you do this enough on average, right, we simply get a pretty good estimate of what the general price of that asset should be. Of course, there may be many buyers and many sellers of this asset. And so this idea leads to this notion of order books. In the order books, we have two types of orders. One is a bid, which is simply how much an agent is willing to pay for a given asset. And then the other one is an ask. And it simply says how much an agent is willing to sell an asset for. A given trusted party, right, essentially keeps a record of all of these bids and asks. And then when someone says, look, the asset is worth, I think that asset's worth $2, so I'll buy it from you for $2, and someone says, I'm selling it for 1.5, then that trade is executed. Namely, when the highest bidder bids more than the lowest asker, right, that trade immediately goes through. And often for pricing reasons, we'll say, look, that is the current market price of this asset, right? Of course, I've kind of swept a few things under the rug, and this has disadvantages for DeFi systems or decentralized finance systems, right? And there's two big ones. Perhaps the largest one is, look, we say kind of very casually, yeah, a trusted party keeps a record of all bids and asks, but that's a pretty large requirement for these general systems because we pay a pretty penny for both storage and compute. And then the second thing that we say, again, we sweep it kind of casually under the rug, is say, look, when the highest bidder bids more than the lowest asker, but that usually means that the price often updates slowly. Especially in many cases when there aren't really a lot of agents trading on, when agents can't necessarily agree on a given market price. So there's this kind of crazy idea that came up. Originally, I think it was introduced, the earliest reference of this I found, better said, was introduced by Savage in 1971, but it was popularized by Hansen's logarithmic market scoring rule, or LMSR, in 2002. And it's rather simple. It says, look, forget this whole notion of order books and kind of complicated matching, oh, we have to match the bids to the asks that are correct and all of these things. Rather just simply say, look, let's let a formula determine the asset price. In this case, then the market makers or third parties are just going to pool their assets into kind of just boxes that they keep as part of the market making process. So we'll call these assets A and B, and we'll call these boxes reserves. And the formula simply maps the reserves to a given price. And it says, look, if the price is set too low, then agents will buy from the reserves at the given price. And if the price is set too high, then agents are incentivized to sell to the reserves at the current price. Then this idea can just simply be extended to say, look, let's just set the price based on the assets remaining in the reserves, right? Look, if too much of asset A is there still, then that means that in some sense, we have overpriced the asset. Right? So just simply reduce the price, which will incentivize people to buy it. The simplest example, and it's kind of a dumb one, it says, look, our function, all it's going to do is it's just going to report a single number for these reserves. That's kind of dumb, of course, because it incentivizes people who believe that number is too high to just simply deplete your reserves, to dump all of their asset into your reserves. And if the number is too low, if the price is set too low, then they'll just buy you out, right? So in some sense, we need the function to very carefully depend on the asset ratios or the asset prices. In particular, if the function is exactly just reports the ratio of the remaining assets in reserves as the current price, right? So if it says, look, the current price is set by the amount of asset B in reserve divided by the amount of asset A in reserve, right? then it turns out that has the right properties, right? If somehow there's less of asset A, then the denominator goes down, right? But the whole thing goes up, right? So in some sense, we've increased the price of asset A, meaning that people should either sell to it or buy less of it. And this curve actually exactly is Uniswap. In fact, you can prove that of the set of all possible curves, the exact one that matches this definition is exactly just Uniswap. This is kind of a weird presentation for a lot of people because I think people are used to what I'm about to give next, which is the definition of constant product markets. But as before, as I said, these two definitions are exactly equivalent. So in a constant product market, right, a trader, let's say me, is only allowed to put in or take out reserves if the amount that I take out and put into each individual reserve satisfies the following property. Before the reserve, there's the product of the current reserve amounts must be equal to after the trade, the product of the reserves after the trade. So in other words, I start with the market starts with some reserves, R alpha and R beta, right? The product is some number K. Then after I perform the trade, I have added enough reserve into R alpha and removed enough reserve out of R beta such that the remaining product is the same, is equal to K. Of course, in the case of decentralized finance, we'll simply assume that alpha and beta are coins, but they technically could be any asset. And you can show, as I said before, that equivalently, the reported price is, in order to satisfy this equation, the marginal price or the reported price has to be exactly the ratio of the reserves. So first things first, why should we give a damn about this kind of, Uniswap? I mean, it seems a little simple, right? It seems simplistic. It's like, look, you're taking the product of two things and you're essentially just keeping it constant. In fact, what's surprising is there's about $52 million as of 11 a.m. yesterday, which I promise is not when I started this slideshow, locked into this kind of decentralized finance, this exchange, right? Another reason why is that there are several protocols starting to use it as a price oracle. And this is good and bad in some senses. And it's, as we kind of found out from the BZX attack, but more generally speaking, it means that this protocol is probably, or this general, let's call it an automated market maker, is worth analyzing. So we'll provide a quick version of the claims of the paper. There are a lot, and they're sometimes very nuanced. They're kind of careful. So I would highly recommend you read that instead if you kind of have any questions about the math. But most of it is pretty simple, and so it should be fairly readable. So first things first, how do we actually formalize this idea that the reported price of Uniswap should be close to, some weird platonic market price? The simplest way to do that, and kind of a common way, is to just set up a game. And in this game, we have an agent called an arbitrageur. In this case, the arbitrageur is allowed to borrow any amount of coin they want. The only condition is that they have to pay it back after they perform the transaction. This should sound very familiar if you have heard of flash loans and all of these things. And then the agent, the only thing they're allowed to do is trade between the two markets. They're either allowed to trade with Uniswap or some infinitely liquid reference market whose price is fixed. So they could always trade coin alpha for coin beta at a given price, and we'll call the price the market price, or MP. So the question of this game is now, of course, what's the optimal strategy, right? Naturally. One way of phrasing this is there's a very simple optimization problem. In this problem, the agent takes out a loan of delta beta, coin beta, and then trades it with the Uniswap market, and then sells it back to the market trades delta beta coin for delta alpha coin, and sells delta alpha coin back to the market for the market price MP, right? This is the trading part with Uniswap is given in the constraint, and then the agent simply seeks to maximize the difference of how much they sold versus how much they borrowed. They have to pay back delta B, if you remember. So in particular, the agent is simply maximizing, how much money they can get by just performing a single trade to this market after paying back the loan. It can be shown, in fact, that the optimal trade always satisfies the fact that the ratio of the near reserves must be equal to the market price. And if you remember from Uniswap, the ratio of the reserves is exactly the reported price of Uniswap. So in fact, the best thing an agent can do by simply trying to maximize their own profit, right, is to make the price of Uniswap equal to the market price. This game also lets us ask another kind of weird question relating to these attacks. And it's, look, I'm an agent who is trying to manipulate the price reported by Uniswap. But of course, I'm faced with these arbitrageurs, these people who can just make free money, right? If the price diverges from the true market price, as we showed previously. So how much does the manipulation actually cost? One simple per block, and I will mention this very carefully, bound can be given. And it says, if we want to increase the price of the market to epsilon% above its current price, then the cost will be essentially proportional to the reserves times the minimum of the percentage squared and the square root of the percentage. This is kind of a weird statement, but it says, look, if epsilon is close to 1, then this is approximately pretty large. This is approximately linear. If epsilon is, on the other hand, very small, this is extraordinarily cheap, right? If epsilon is, we want to manipulate the price to 1% above what what the true market price is, essentially we only have to pay about 10 to the negative 4 times the current reserve value, which for non-liquid coins is extraordinarily cheap. I mean, essentially we might as well say it's free. But more generally though, if we want to make large price manipulations, this starts becoming pretty expensive. So, and I will mention these again. This is a super important point that we mentioned in the paper, which was released several weeks before the BZX attack and all of these things. And this is literally me subtweeting several weird Twitter threads that I had to respond to. We invented the conditions, but alas. Look, the lower bound is 0. As I said, the previous bound is a per block lower bound. So the lower bound is 0 if it can be done within one transaction. Because if the number of blocks is 0, then 0 times anything is just 0. Additionally, manipulation over the short term is pretty cheap, right? It's proportional to the price that I gave, but for relatively small epsilon, that's very cheap. And as I said before, if you want to trade stuff, if you want to change the price by percentages that are, let's say, smaller than 10%, it might as well be essentially free unless your reserves are very large. But there are some good and bad properties as well from Uniswap that are independent of this manipulation. In fact, trading a fixed amount of desired coin is actually always cheaper as the reserves grow. So if the reserves are twice as large for a second market, then in fact your trades will be half the original price or twice as cheap. A weird thing that at least in the feeless case is that liquidity providers are actually only incentivized to add coin to the reserves if they truly believe that the market price is driftless. So they believe that in some sense, the market price will return to its original value at some point in the near future. That often means, this is called, I think, impermanent loss is what I believe the name Hayden gave to this. But more generally, in the case with fees, this can be changed a little bit, but it doesn't, the general idea is that driftless is essentially a necessary condition for an agent to provide any kind of asset into the reserves. And then another kind of nice property is actually it turns out Uniswap can never be drained of coin because the sum of the reserves is always, no matter what you do, no matter how much money you put in or take out, is always bounded from below by the product constant. So as expected, yeah, we talk all this math. This is kind of cute and nice and theoretical, but we might as well simulate it at least. So we simulated it with the Gauntlet DSL, and everything kind of confirms the mathematical results. In this case, we're simulating comparing the market price versus the Uniswap price when Uniswap has fees, which is why the market price and the Uniswap price don't match exactly, like I gave in the previous slide. But as you can tell, I mean, the divergence is 0 from within the bounds. So in the case with fees, you don't get exact results. You get that the price should lie within some interval of the true price. And in fact, we do see that. Even in the presence of noise. So even if you add traders who simply are incentivized to trade with Uniswap if the difference in price is small, it turns out that the Uniswap and the market ETH price are pretty much, I mean, on point in the presence of arbitrageurs, of course. And kind of a not so great thing, but reiterating the same point I made previously, is that even in the case with fees, the initial LP utility versus simply holding the portfolio, the equivalent portfolio of coins, at some point 0, and then this is evaluated at time t, right? As you see, essentially you only really have positive payoff if the asset is driftless. If it's not driftless, you are pretty much screwed. And you can tell this is given right here. And in particular, it diverges on the right simply because sampling error scales as a square of the deviation. So this gives, this is why you see some weird white boxes which shouldn't fully be white, but whatever. The idea is, of course, as is required, the asset is driftless, and even in the low noise case, you still kind of lose money. So anyways, just wanted to give a few acknowledgements to a lot of people who have made this possible. Dan from Paradigm, Hayden from Uniswap, of course, Regina, who found some interesting mistakes in the appendix in the first version of the paper, Alex from Placeholder, Jonathan from Stanford. I'm not even kidding. Reviewers 1 and 2 gave some great comments and great feedback, which really helped improve the paper quite a bit. And Sid from Dover, who helped edit the slideshow. Anyways, yeah, thank you.
All right, thank you, Guillermo. It's great to see reviewer 2 get a shout out. That's a nice thing to happen. Really interesting talk, and I think Uniswap was an example of just one of these sort of new institutions that has emerged, very recently. That I think is going to be a lot more important going forward. And the first question I want to ask is, how does this generalize to other Uniswap-like mechanisms? The analysis that you've done.
So we do actually generalize slightly. So we generalize to, in fact, it turns out there's this kind of crazy new version of Uniswap, which is you can trade arbitrary amounts of coins. So n coins to n coins. It's called Balancer. And in fact, the analysis as given in the paper also generalizes immediately without pretty much any change in the derivation. There's this crazy thing that Tarun and I have been working on called constant function market maker. So you can generalize this class very simply to a huge class of possible market makers who all essentially have the same properties that Uniswap has, except you get to define the curve. So in this case, we said, look, the curve is defined by the fact that the market price must be the ratio of the assets, but you can make it essentially any function you want. And you still get like these very, very nice properties where it says arbitrageurs are incentivized to make the market's price match the true reported price and all of these things. So it is certainly possible, but I'm gonna give that one. I'm gonna punt it for I don't know, if we're not careful, about 2 months or something of the like, and then there may be some results there.
Good to hear. Thank you. Wasim.
Hey, Guille, it's Wasim. Just a really quick comment, because I noticed on your acknowledgements you thank reviewers 1 and 2. So yeah, that's quite unusual to see that reviewer 2 seemed to be quite nice. So I just wanted to make the point to everyone that's watching at home and in the room that our reviewer 2, even our reviewer 2, is nice. So please send your papers for our upcoming call for papers. Opens 15th of March and closes 31st of May.
Yep.
Thanks so much for that. Just curious to see how you'd think about this with like a Uniswap layer 2 solution. So both, I guess, in terms of the scaling part of it, but also in terms of, I guess, you not having to use ETH as a asset for all those, and how this would potentially extend to the other pools now on Uniswap 1 that have to use ETH as the other currency.
Sorry, I'm not sure I understand the question fully.
Yeah, I guess just Uniswap v2. Like, how does this kind of layer 2? How does what you do here? How would you kind of project any of the findings from this onto that? I guess the 2 areas that I was thinking in terms of just the number of transactions and the speed, and the fact that you would have to lock up some funds if they're using that as an oracle. Would that change it? And then 2, just in general, since this is the ETH USD price, obviously you can use a stablecoin on that in Uniswap, but I'm just wondering for the other assets that are not ETH, right, you have to match them with ETH, and so I'm wondering if there's any findings or anything you can draw out in terms of that too.
So very generally, actually, we show. So I'm not 100% sure about your question 1, so I'm gonna punt that unless I can somehow process it. But for question 2, very generally, actually, the numeraire is kind of independent. So it turns out you can form a graph of all the possible trades. And then it turns out another thing that's actually very efficient to solve, which I'm surprised that no one's doing yet, is to solve the overall arbitrage price on the overall arbitrage problem on the graph. So even if there aren't any pair, so as we say, look, we have to compare DAI to ETH. In order to compare DAI to another currency, I don't know, WBTC, for example, right? We have to go through this intermediary of ETH, right? But technically speaking, the problem so the price of A divided by B and B divided by C should actually be the same as the price of C to A directly along any path. And the reason why is because the arbitrage problem is easy, and the arbitrage problem tells you necessarily that these two prices will match directly. So interestingly, it actually doesn't matter what the path is between any two coins and whether it includes ETH or not. It should actually, so long as the value of ETH is literally not 0, these all should match. So I think, I don't know if that answers your question exactly, but the point is that somehow the numerators don't matter at all. It's kind of very nice in that way.
Hey there. I'm wondering, does this enable the possibility of markets with 0 fees and 0 slippage, or am I mistaken?
So there's always slippage in this case, right? Because you require slippage in order to actually change the market price. If your slippage is 0, what you're saying is essentially that your market price is fixed, which is not good in this scenario. It does in some sense enable arbitrarily low slippage, depending on the amount of reserves. And in the case of feeless markets, sure, it might enable those, but there will have to be weird incentives. So as I said, liquidity providers will only provide liquidity to feeless markets if they believe that the market price is a recurrent process. So if they believe that the market price will return back to its original value. So it's unclear what that means, very generally speaking, right? Like whether, we could have some subset of the population which believes that the market price will always return back to, their current investment price. And then we have some subset of the population who just simply trades with this. So it's kind of not, that's not a fully fleshed out question. And there seem to be kind of a bunch of different incentives, which have to align in the right way for there to be both fee-less markets and, arbitrarily low liquidity or arbitrarily low slippage markets. This doesn't either preclude that nor imply it. It just kind of says something about the case for both of them. Does that make sense?
Yeah, that totally makes sense. Thank you.
Okay.
Your description of Uniswap markets reminded me a lot of the Paramutual betting that you see at a horse track. Are they really the same thing? And if so, are the attacks that odds manipulators use similar to the attacks you would use on a Uniswap market?
So I'm afraid I'm not very, I guess if you give me a quick description maybe, but I'm not sure what these markets are, like the odds markets on horse racing.
Yes.
I don't know exactly how they work, so I'm afraid I can't say much. But I mean, I guess if they work in a similar way, the answer is yes. You could technically perform the same attacks, right? Where if you have two pools. So this is how I suspect it works, right? You have two pools, and then people simply put into the pool, and the odds change based on that, assuming no fees or something, right? Yeah. In that case, that both things are, I guess, or the same attacks would apply for both in a way that is essentially, equivalent. And this is how you could just manipulate horse markets, in the same way that you can manipulate an oracle like Uniswap. So it's not clear what you can draw from that, though.
Hi, thanks for your presentation.
Hey.
Observationally, we're seeing that a number of projects are using Uniswap markets to kind of bootstrap issuance of their token.
Mm-hmm.
And the kind of emerging bonding curve literature is kind of talking about this directly, programmatically issuing tokens. It seems like these two areas are going to be convergent soon. Do you have any thoughts on what that might look like?
Wow, there's a lot of weird questions I've never thought of. It's interesting. I'm sorry for context. I'm a mathematician by training, which is why I have just started getting into this. That's a good question. I suspect that both of them will actually look relatively similar. There does seem to be a weird correspondence between kind of the token bonding curves that we think of normally and these automated market makers for pricing. It's unclear if there's an equivalence. But my suspicion is that they'll actually look surprisingly similar because it seems that the incentives are the same, or at least at a surface level, at a first order approximation, they appear to be roughly the same. I'm not sure if that fully answers your question. I think it's a bit vague on my end, but hopefully that kind of, my suspicion, in the same way that like, automated market makers are equivalent, to some weird limits of some order book methods, is that these two things are equivalent in a similar sense. If you could take mechanisms for bonding curves and actually generating tokens and use them in some specific way for like actual pricing, right? In some sense, it's our duality there.
You mentioned impermanent loss and that it's sort of like a fool's errand to provide liquidity on Uniswap. So how do you reconcile that with the fact that there is $50 million of liquidity locked in Uniswap?
That's a great question. Honestly, maybe I shouldn't say this because somehow it feels like weird, but I have no idea. The fee is really not large, so to me it's surprising, I will say. I don't know. I mean, maybe there's just like a widespread belief that ETH is just going to be stable, or that any of these stable coins are going to be stable. I guess stable coins make some sense, but not even with respect to ETH. So I'm honestly not 100% sure. I'm not actually sure about this. And this is something that's kind of been bugging me in the back of my head for quite a while. It's one of those weird things where sometimes it feels like people are gaining from fees, but not relative to an actual portfolio of just holding. So they are gaining, and there is a non-zero. I mean, you can compute exactly what the gain is, in fact, but it's not clear why this would be better than just like a simple Markowitz optimized portfolio or just even like a HODL portfolio. So I'm afraid I'm not sure.
I do have two thoughts on it. One is that synthetics actually incentivizes liquidity on Uniswap, and two is
sure.
MakerDAO actually shut down Oasis DEX right before Uniswap launched. Yeah.
So yeah, this is fair. I mean, like there may be like secondaries. I just don't know why it would be the case. As T goes to infinity speaking, right? Like it's not obvious to me that this should be or would be the case, but it seems to be. And for sometimes synthetics makes sense. But if this was to become the reference market, then what happens then? I'm not sure.
Hi, thanks for your presentation. I'm wondering if you've thought at all about how to set the optimal fee rate or set the appropriate constant function in a Uniswap-like market in order to maximize returns for liquidity providers?
Yes, this is actually a great question. I have thought a decent amount about it. There's two kind of things about this. Is one, you have to have a market model, right? You have to have a trader model. So those two things are big questions. And essentially what you're doing is you're trading the problem of setting a fee, which is a problem of setting one parameter, to the problem of setting a model. You can do it. In fact, actually, we showed that there's many functions that you can make, kind of constant function market makers. So you can actually just simply phrase it as an optimization problem where you write down exactly what the expectation of liquidity providers are subject to the distribution that you pick, and then simply optimize the parameter based on that, or simply optimize the function based on that. It is possible. It's not easy. My suspicion is that, in fact, it's probably computationally hard, but in one dimension, it's probably pretty close to the true global optimum. No one has done it yet. We haven't done it either. It might be something interesting for someone to try, if anyone's interested. But very generally speaking, yeah, it's something that someone should definitely do. My suspicion is actually Uniswap is pretty good in that set of classes, and you probably can do a lot better. But it's also not obvious that that's true under distributions that people care about for market prices.
All right, thank you, Guillermo. Unless there's any other questions, we'll wind that up there. But look, absolutely fascinating, timely, important research. And thank you very much for presenting that.
Thanks.
Cheers.
Thanks.